Chem 213, Organic Chemistry, Exam 3 Material, Part 2. We're going to go ahead and go through all of Chapter 19 in your textbook, Aldehydes and Ketones, and also Nucleophilic addition reactions. Aldehydes and ketones are characterized by the carbonyl functional group. We have with an aldehyde, on the carbonyl carbon, there's going to be a hydrogen for an aldehyde, where we don't have that for a ketone. So the R groups in a ketone can never be a hydrogen, otherwise it reverts back to an aldehyde. Now the smallest aldehyde, this R group can be a hydrogen, and that would be the smallest of the aldehydes, but keep in mind on a ketone these R groups cannot be hydrogen. These compounds occur widely in nature as intermediates in metabolism and biosynthesis. Now, aldehydes and ketones, in every organic textbook, they're always separated from the other carbonyl groups. And that's because aldehydes and ketones are bonded to substituents that cannot stabilize a negative charge and therefore cannot act as leaving groups. What is meant by that is on the left side or right side of this carbonyl group in the ketone that I'm showing you here, you only have carbons to the left or to the right, just carbons. You don't have something more electronegative as you do, for example, in esters or amides, where you have a nitrogen or you have an oxygen. So keep that in mind. That's why these are separate. You have just hydrocarbons on the left or right, and those cannot stabilize a negative charge. And aldehydes and ketones behave very similar, so we'll be taking a look at those together. Let's talk about the different pieces of aldehydes and ketones. You have the carbonyl oxygen, carbonyl carbon, alkyl groups, and acyl hydrogen. And we've talked about this acyl hydrogen before when we talked about proton NMR, if you guys remember that from our spectroscopy section. So the carbonyl carbon is sp2 hybridized and forms 3 sigma bonds. It has a 120-degree bond angle. The carbon-oxygen double bonds are polarized because of the high electronegativity of oxygen relative to carbon. The carbonyl carbon, this guy right here, is positively polarized. It's electrophilic, a Lewis acid, and reacts with nucleophiles. Conversely, the carbonyl oxygen, this guy up here, is negatively polarized and nucleophilic, known as a Lewis base. Physical properties of aldehydes. The melting point of aldehydes varies non-systematically with increasing molecular weight. So this is actually something unusual. Typically, if something weighs more, if a compound weighs more, its melting point is higher. Well, and it increases systematically. Well, this is unusual. The melting point of an aldehyde varies non-systematically. So this means I can't predict only on molecular weight if one aldehyde will have a higher melting point than another aldehyde. I can't predict that. It's non-systematic. Aldehydes have higher boiling points than the boiling points of alkanes of similar molecular weight due to the dipole-dipole interaction. So on the previous slide, we commented that the carbonyl carbon is slightly positively charged and the oxygen is slightly negatively charged. So what happens when these guys get together in the liquid state, because we're talking about boiling points here, when they're in liquid state, the polar oxygen here will have a polar dipole-dipole interaction with a carbonyl group on another molecule, and that to another one. And what this does is it causes them to have an intermolecular force, a dipole-dipole interaction, that makes their boiling points higher. That means in order to get this molecule, for example, off on its own as a gas, it has to overcome this interaction also. So it takes more energy. The boiling points of aldehydes are lower than the corresponding alcohol due to the lack of hydrogen bonding. So what this tells us is we do have 2 intermolecular forces now mentioned. Up here we have the dipole-dipole interaction that happens with aldehydes, but we're also looking at the hydrogen bonding of alcohols. So what they've done is they've ranked them for us. We now know that hydrogen bonding is a much stronger intermolecular force than dipole-dipole interaction. That's what this is telling us also. Now we do have a systematic increase of boiling points with molecular weight. I want you to contrast this with letter A. So letter A says non-systematically melting points of aldehydes varies non-systematically with increasing molecular weight, but it increases systematically for boiling point. That's normal. That's what we're used to seeing. So far, the only unusual piece is letter A here. We would be able to predict the boiling point. If it has a higher molar mass, it would have a higher boiling point. We are able to predict that. Physical properties of ketones. The melting point of ketones is systematic with increasing molecular weight, so that is what we expect. The more it weighs, the higher the melting point is. That's something I can predict with ketones. Ketones have higher boiling points than boiling points of alkanes of similar molecular weight, and that has to do with that dipole-dipole interaction we saw on the alkane section. It's the same thing for ketones. And the boiling points are lower than the corresponding alcohol due to the lack of hydrogen bonding. That's exactly what we saw also in the aldehydes, and again for the same reason. It's the intermolecular force of dipole-dipole interaction that causes it to be a little higher than alkanes, but remember the intermolecular force of hydrogen bonding is stronger than the dipole-dipole. So that's the same as the aldehydes. And there is a systematic increase of boiling point with molecular weight. So going back and taking a look at this melting point thing between aldehydes and ketones and boiling point. They all behave as expected with the exception of the melting point of aldehydes. So we have an increase with molecular weight, increases the boiling points of both of them. An increase of molecular weight increases the melting point of ketones systematically, but it does not do that with ketones. Here we have, again from that website that I like, Compound Interest, and I have the link over here again for you, is the aroma of fresh baked bread. And I noticed on this poster that they made that there's both aldehydes and ketones represented here. So you might want to take a look at this. I thought this was pretty interesting. So as I was looking up ketones, I've heard of ketones before when they've talked about biochem and what happens in your body. So I wanted to look up a little bit about ketones, and I found some information of ketones with talking about diabetes and bad breath. So I thought this was an interesting thing to bring in here. So what are ketones? Biochemical interest. They're basically when your body begins burning fat instead of carbohydrates for energy, it also is tied to the amount of insulin in your body. So I thought I'd put this in here. So if you want to take a look at this, I put the link to the main article on here about type 1 diabetes and type 2, and I thought you might want to take a look at that. This particular slide is not on the exam, but I know a lot of you are going into the medical field, and so I wanted to include this for you so you can take a look at that. All right, nomenclatures of aldehydes and ketones. Let's go ahead and start naming these. Aldehydes are named by replacing the terminal E of the corresponding alkane name with an AL ending. The parent chain must contain the aldehyde group, and the carbon of the aldehyde group is always number 1. Now, if the carbon is attached to a ring, we actually use a totally different naming system. We're going to see this also when we talk about carboxylic acids. So when you're naming a compound and an aldehyde is on a ring, the name is going to change to have a suffix carbaldehyde. So we'll have some examples of that. Table 19.1 in your textbook gives you some common names of aldehydes. So on these common names, formaldehyde, you're definitely going to see that one before. In fact, you most likely know formaldehyde more than you do methanal. That's its common name when you have one carbon. Acetaldehyde is also a very common name. You need to know that common name. And then benzaldehyde on the common name is one you already know from the benzene section. So of these common names, there's 3 of them you are responsible to know. And with the systematic name, you need to know all of those. Notice we took off the E ending and put AL. Notice that every time we have an aldehyde, this is carbon number 1, so we do not indicate the location of the aldehyde. We know it's on one, it's understood. And then I like this example here where it shows you a carbon-carbon double bond. and that is included in the name. If you take a look here, we have the E right here for propenal. And remember, this is already carbon number 1. You cannot have a carbon-carbon double bond between carbon 1 and 2. There's just not enough room. So the only place the double bond can go is here. That's why you don't state where the double bond is. And then the common name benzaldehyde you've seen before. Its systematic name, because it's on a ring, becomes benzene carbaldehyde. You're still definitely able to use benzaldehyde. You'll probably hear that a lot more than you will benzene carbaldehyde. But I wanted to highlight the fact that the systematic naming, when a aldehyde is on a ring, it is named using the suffix carbaldehyde. So I have a bunch of names here. I want you to go ahead and provide structures for the following. It's best for you to go ahead and pause the video, go ahead and draw these structures, and when you're done, come back and check your work. All right, so let's take a look at these. We have pentanal as the parent, so I'm going to have 5 carbons in a row. 1, 2, 3, 4, 5. My aldehyde group is going to be coming off of the number 1 carbon, and the accepted abbreviation for an aldehyde is CHO. It can't be OH, it has to be H and then O, so be careful with that. Coming off number 2, carbon 1, carbon 2, would be a ethyl group, CH2, CH3. And then coming off of number 4, remember this is 1, 2, 3, 4, I would have a methyl group, CH3. So checking my work, do I have an ethyl off of 2? Yes. I have a methyl coming off of 4. I've handled everything. I will go in and complete this by putting in the proper number of hydrogens. This gets 1. And I know it's a little sloppy. Yours I'm sure is much neater than mine. But I wanted to go ahead and draw this first because most likely this is how most of you did it. You have 5 carbons. I tend to put my carbonyl group on the right-hand carbon. I think it's because it's on the end of the name is why I tend to do that. I tend to work backwards. So what you should have is 5 carbons, and this is carbon number 1. Coming off of 2 would be an ethyl group, and off of 4 would be a methyl group. So I actually want to erase this, and I want to show you the same compound, but a different version. So I know this looks different than the other version, but this is a structure I'd like you to go ahead and draw somewhere else where if someone were to present this format, would this throw off your naming it? Let's say instead of you given the name and you draw the structure, if you were given a structure like this, you need to be able to generate the name. So what I want you to notice is this is carbon number 1. No matter what I do, the carbonyl carbon of the aldehyde is carbon number 1. So my longest continuous chain in this case happens to bend around. And now I have on carbon 1, that's again where my aldehyde is. On carbon 2, do you see this ethyl group here? And on carbon 4 is my methyl group. So the numbering would go in this direction here. So don't let formatting throw you off. If someone puts it in an unusual format, you know the rules. You know that an aldehyde, the carbonyl carbon is always number 1. Find your longest continuous chain and go from there. Don't let formatting throw you off. All right, let's take a look at cyclopentane carbaldehyde. So did you notice that I have carbaldehyde as the suffix, and that's because it is on a ring. So cyclopentane. I have my 5 carbons and I have my carbaldehyde piece coming off of here. This is another way it's acceptable to draw it. Notice I have the double bond O and then the H next to that. So that is another way to draw an aldehyde. 2-naphthalene carbaldehyde. So we haven't seen naphthalene for a while. That was back in the benzene section. I wanted you to practice how to do a naphthalene carbaldehyde. It is on a ring. Taking a look at my naphthalene, remember in this valley part here, there's already 4 bonds to carbon, so there's no hydrogens here. So you can't add anything. You can't put an aldehyde group here. This is the first place I can have something. In this case, if I wanted in one naphthalene carbaldehyde, it would be here, but this is a 2, so it's coming off carbon 2. So remember, on the numbering system on naphthalene, you don't count the valley, you start off at the peak and then work your way around. I also want to remind you that a naphthalene is very symmetrical, and so the peak here or here, this would be carbon 1 or 1, 1 and 1. Here's 2 and 2, 2 and 2. So what could happen if you're going to have an aldehyde on a naphthalene, you're basically, if there's only one on there, you're only going to have either a 1 naphthalene carbaldehyde or a 2 naphthalene carbaldehyde. Right, benzaldehyde is one we've had before. Ethanal or acetaldehyde, that's actually one earlier we saw that you needed to know the common name acetaldehyde because that's what you see more often than ethanal. We only have 2 carbons with my OH double bond O and H group here. This is carbon number 1. And propanal. All right, to name ketones, we replace the terminal E with ONE ending. The parent chain is the longest one, which contains the ketone group. So that's very similar to when we had alcohols. Remember, when we had alcohols, it's whatever direction the alcohol would have the lowest number gave it priority. Well, that's what's going to happen also to a ketone. So numbering begins at the end near the carbonyl carbon. We also have common names for ketones. They're given in alphabetical order with the names of the groups attached and then adding the word ketone. So what I want you to do for these 4 compounds here is to provide the structures for the following. This again would be a time for you to go ahead and pause the video, fill in your answers, and then come back and check it. All right, let's take a look at this. 3-hexanone, 1, 2, 3, coming from right to left. I have it coming off of number 3. Also, if we take a look at this and we did the common name, it would be ethyls on this side, propyls on this side, so it would be ethyl 1-propyl ketone. So acetone is a common name you definitely need to memorize for ketones. Its IUPAC name or systematic name is propanone, and its more common name is dimethyl ketone, but acetone is the one you're going to know it by more often. Now, I want to mention something about this dimethyl ketone. Take a look at this name here. Methyl's on the left-hand side and also on the right-hand side. That's where the dimethyl ketone comes from. So the ketone group is this group right in here. So when they named this acetone, we have commented before that ACET means 2 carbons. Well, I see 3 carbons here. So what I think happened when they decided to name this common name acetone is they probably figured the ONE part here accounts for this carbonyl carbon, and the ACET means 2 carbons, one on the left and one on the right. Not quite sure, but I'm trying to reason through why acetone has 3 carbons. Again, I think the ONE is talking about the ketone feature, just like in the dimethyl ketone. Notice this is handled here. So I'm pretty sure that's where that came from. All right, if you also have a double bond involved, remember that the ketone has higher priority. So we're going to go ahead and, in this case, split up the name. The E right here is telling me that there is a double bond starting on number 4. But what has priority is the ketone, so it gets the lowest number. That's why this is a 4-hexane 2-one, because ketone has priority over a double bond. And then this last one, I wanted to challenge you on what would you do if there's more than one there. Did you notice this E came back whenever we have a multiplier? In this case, it says I have 2 ketone groups, 2 ONEs, and we did the same thing when we had 2 alcohols, but I have to tell the reader of the name where are they located. So the 2 and the 4 tell me where the 2 ketone groups are on a parent chain of 6, all single bonded. There's a lot of information in that one name. So when aldehydes and ketones do not have priority, we change the name. This is known as an acyl group, so be sure to add that to your functional groups. An acyl group is when you have carbonyl group with R here, and then we're not specifying what's here. If you remember when we talked about the aldehydes, when a hydrogen was right here, remember we called that an acyl hydrogen, so that's the acyl position. Now, the common names, when they don't have priority, this is acetyl, this is formyl, and this is benzol. Just when you thought you had every name you could think of with benzene, they found another one for you. So there's another one, benzol. The prefix oxo is used if other functional groups are present and the doubly bonded oxygen is labeled as a substituent on a parent chain. The previous pieces up here is when we have, this is like the common name, like when we had isopropyl, remember those? That's when you would use these. Now, this is more the systematic. So take a look at this. I kept this. This is from your textbook, and I like the colorized of it. So what this name does is it assumes you know how to name esters, and I know you haven't been taught that yet. So I want you to see that right here is your ester group, right here. An ester ends in an O8 ending. So again, even though we haven't talked about it in the textbook yet, you do need to understand a little bit about the naming of an ester group. So do you see this piece on an ester? We have carbonyl group, oxygen, and this would be the R group. This group right here is this piece right here, and there is a space. There's no dash, no comma. There's actually a space right here. So this methyl group, specifically this methyl group here, is this group right here. It's the right-hand side as this ester is written. It's whatever size this is. This is carbon number 1 still. And what's going to happen relative to that, this is getting an ester, this is carbon number 1. Coming to the left on carbon number 3 is where I have my ketone, and that's this oxo. So when the ketone definitely does not have priority, it's known as an oxo. And then we have 6 carbons going away from that. And notice 1, 2, 3, 4, 5, 6. There's no double bonds, all single bonded. So that's how this would work. All right, so I have both aldehydes and ketones here. I want you to go ahead and draw the following. Pause the video, come on back, and see how you did. All right, pentanal, 5 carbons, aldehyde, carbonyl group on carbon number 1. No substituents, just pretty straightforward. 2-pentanone, 1, 2, 3, 4, 5. Its systematic name is 2-pentanone, and then its unsystematic name is methyl 1-propyl ketone. Again, I think the 2-pentanone in this case would be easier to do. It's usually when they're simpler, like even smaller than that, that you would go ahead and use the other name with ketone in there. Cyclopentanone. This is when we have a ketone coming off of a carbon in a ring, and it's kind of an interesting thing to draw when you draw it for the first time. But yeah, you definitely just bring those 2 lines coming out of the corner there and put the oxygen on there. Here is an example of both an aldehyde and a ketone together, and I wanted to show you how to do that. So what they've decided is the aldehyde still gets to be the parent and be carbon number 1. Did you notice the Al ending? So I have 1 carbon here, there's a 2nd carbon here, and a 3rd carbon here. That's where the propanal comes from. Oxo, because my ketone does not have priority, is coming off carbon number 2. So this is an example of when you have both an aldehyde and a ketone together. Cyclohexane carbaldehyde, again keeping in mind when the aldehyde is on a ring, the suffix becomes carbaldehyde and the carbon it's attached to becomes carbon number 1. 3-pentan-2-one, I wanted again to have you practice when you have both ketone feature and also a triple bond. Ketone has priority over triple bond. So with this set, I want you to go ahead and generate the names. So go ahead and name these, pause the video, name these, come back and check your work. All right, this first one here happens to be a ketone. Methyl ethyl ketone is its common name. In fact, I don't have it on here. This would be 2-butanone if it had its systematic name. But the reason why I didn't include that is this is one of those common names, again, just like isopropyl alcohol, it's known as MEK. This is a very common solvent, And what I think is interesting is its simple name, ethyl methyl ketone, E comes before M, but in its abbreviation, it's always MEK. So when I worked in industry, I used this as a solvent a bunch, and it is known as MEK. It's just not alphabetically correct. So just know MEK is ethyl methyl ketone. With this one here, I'd have that CH3 group 2 times, so you know that there's going to be a substituent coming from here. This is an aldehyde. I have the aldehyde group on the left-hand side this time, and a methyl group coming off of carbon number 2, so it's 2-methylpropanal. So we have on this next one an aldehyde again, and I have my methyl group coming off of carbon number 3. Again, remembering that in an aldehyde, this carbon on my carbonyl group is always carbon number 1. So down here I have a cycloketone, and remember the carbon right here is going to be carbon number 1 because it has priority, and you go in whatever direction that causes the chloro to have the lowest number. 3-chlorocyclohexanone. 2-bromobenzaldehyde, or we can use the ortho system on here because there's just 2 things on a benzene ring, so it could be either 2-bromobenzaldehyde or ortho-bromobenzaldehyde. And here we have another aldehyde with a double bond. 2-pentanal. Remember, the aldehyde's understood to be on carbon 1. Relative to that, the double bond starting on carbon number 2. Preparation of aldehydes and ketones. The best method of preparing aldehydes and ketones is alcohol oxidation. Primary alcohols are oxidized to give aldehydes, and PCC and dichloromethane is usually chosen for making aldehydes. Now, my general reaction here, I do have a primary alcohol. Normally, you wouldn't draw a primary alcohol with explicitly showing all these bonds, but the other thing that I'm showing you in this general reaction is we're going from an sp3 hybridized carbon to an sp2 hybridized carbon. So that's the reason to show this. You normally would not have to show all these explicit hydrogens and all that. Normally, you would just write it as a condensed structural formula. So the best way to make an aldehyde is to take a primary alcohol, PCC, and I can make the aldehyde. Don't forget, you still also need to put the dichloro here, the CH2Cl2. So primary alcohols are oxidized to give aldehydes, secondary alcohols are oxidized to give ketones, and we can go ahead and use PCC. We can also use CrO3, and the sodium chromate also are all effective for making ketones. So in this case, I have a secondary alcohol. Again, I'm explicitly showing you this to show you it goes from sp3 to sp2, and again, we make a ketone. We are going to see this reaction a bunch as the semester goes along. In fact, right now we're taking a look at making aldehydes and ketones, and when we were back in the alcohol section, we actually talked about primary alcohols reacting to make aldehydes. Well, now we're looking at how are aldehydes made. So this is the same reaction you saw before. Same thing with secondary alcohols. We could make ketones. Well, now we're looking at from the viewpoint of how do you make ketones. So these are the reactions, these kind of reactions we're going to see again and again. All right, we can also now, this is another reaction, we can reduce an ester and we can go ahead and make an aldehyde. So this right here is diisobutyl aluminum hydride, DIBAH. So instead of writing all of that, we get to use the initials. They're also using toluene and negative 78 degrees C. That's the first step. The second step is a protonation. So we're going to be making an aldehyde out of this, and this is a reduction. So if you keep in mind, a reduction reaction means we're going to have less bonds to oxygen. So what do you predict the product is going to be with this reaction? What's going to happen is this OR is going to become an alcohol, and then we're also going to make an aldehyde. So the breaking point is going to be right there. We're going to make less bonds to oxygen. So this is a reduction reaction. So not only do we get an aldehyde, but we actually also get an alcohol out of here. Don't forget ROH is an alcohol, just written in the reverse as we're used to. All right, we can go ahead and make ketones with ozonolysis of alkenes. Now, we do have a condition that has to happen. It says if one of the unsaturated carbon atoms is disubstituted. So this goes back to last semester. It's reviewed. You can review this again in section 7.8. And what's going to happen is we have two hydrogens here. So this is going to be unsubstituted. This is disubstituted. And what's going to happen is this ozonolysis, it's basically going to form a cleavage reaction where it's going to break this right here. It's going to cut it right here. So we can get a ketone here. And technically, not only depending on what's going on this carbon here and this carbon here, we actually also got an aldehyde out of that. But this is focusing, the way they're wording this is they're focusing it on making a ketone. But again, depending on this cleavage reaction, what's on the left or the right, you might get two ketones, an aldehyde ketone. Be sure to review section 0.8 to see the specifics of this reaction. Another way to make a ketone, we learned this back in section 16.4, is a Friedel-Crafts acylation of an aromatic ring, aluminum chloride in the presence of some heat. So go ahead and I would have you pause the video and go ahead and write the product on this. You've seen this one before, so hopefully you remember that pretty well. And there we have Friedel-Crafts acylation. The connecting point is where the halogen was. And we also have the hydration of a terminal alkyne in the presence of a mercury catalyst to make a ketone. This is again a terminal alkyne. Make sure you keep that in mind. It must be on the end. And what we actually get is a methyl ketone out of it. And this is a reaction we had back again in section 8.6, so you can go back to that section if you want more detail on this. And this is a functional group, methyl ketone. And if you remember, we saw some methyl ketones a lot when we talked about mass spec. We saw a lot of fragments of methyl ketones. So I have complete the following reaction. The first two of these, I want you to prepare the following product from the appropriate alcohol. I wrote the word form instead of from. All right, so you need to change that to from for me. Since I'm already recording this, it's going to be stuck like that. All right, so here's the name of the product that I want, and the reaction is going to go here. So I want you to go ahead and use the appropriate alcohol to form these two. So the best way to do this is to start at the end. Give me the structure of the product first. So that's pentanal. And the appropriate alcohol would be wherever this carbonyl oxygen is, that would become the OH group. But keep in mind, I would have to have two hydrogens here instead of one, so carbon has the correct number of bonds. And I know I'm going to go from an alcohol to the product, so I need to find some reaction conditions. And we saw earlier what different oxidizing agents, so PCC, CH2Cl was one of them. So go ahead, and this happens to be a ketone. Go ahead and use the same format for this. Write down the product, write down the reactant, and then the conditions that it needs to have. In this case, there was actually 3 different ones in there that I could have used. So keep in mind, wherever the carbonyl group is, that's where the OH group is. And then in this case, you could have picked one of 3. I just picked one of them. So go back and check in your notes 3 different agents you could use for that. All right, so for the rest of these, go ahead and complete the following reactions. Pause the video, and I will come on back and check your work. All right, for this first reaction here, what's going to happen is this is an ester, and what's going to happen is we're going to break the bond right here. I put the oxygen on the left-hand side this time instead of the right-hand side. Still an ester, and this piece right here is going to become an alcohol, and this other piece here is going to become an aldehyde. This next one here is ozonolysis. We're basically going to cleave this right here, and we're going to get out of it a ketone, and in this case also formaldehyde. Letter E is going back to our Friedel's crafts, and my R group happens to have CH2CH3, so I made sure I added that. The connecting point is where the halogen is. And this last one here is going to make a methyl ketone. This is going to be the case where I have a terminal alkyne, and it's going to form a methyl ketone. How'd you do? Oxidation of aldehydes and ketones. Ketones are usually unreactive towards oxidation, and this reactivity is a consequence of structure. Aldehydes have a hydrogen or a proton that can be removed during oxidation, but ketones do not. Ketones are inert to most oxidizing agents, but can undergo a slow cleavage reaction when treated with hot alkaline potassium permanganate. The reaction is practical for cleaving symmetrical ketones. So one of the things we're going to do is when in lab, we can actually do an oxidation reaction. If we have a compound and we know it's either an aldehyde or ketone, but we're not sure which one it is, we can use an oxidation reaction to identify it as either an aldehyde or ketone. So we'll be seeing some of those reactions also. Those will be qualitative. So this is the one reaction that is undergoing an oxidation of a ketone, and I happen to pick a symmetrical ketone in this case. Well, it is a symmetrical ketone, but it went on a ring. This is the potassium permanganate. So what you want to do with this, and what helps me, is I count my carbons. So if you take a look here, carbon 1, 2, 3, 4, 5, 6. It's going to break here. This is carbon 1, 2, 3, 4, 5, 6. If you're going to break up a ring, make sure that you don't give me too many carbons on this side, that this carbonyl group here and this carbonyl group here is going to be only 6 carbons total. Don't add more carbons on there. So one of the ways that I do that is I go ahead and make myself some notes here and number them. So this is the reaction of a cleavage reaction treated with hot potassium permanganate. This is one of the reactions that happens there. Aldehydes are oxidized to the corresponding carboxylic acid. So we have our carbonyl group here. This is an oxidizing agent, and notice it's converted to a carboxylic acids. Now, this is hexanal. This is an example out of your textbook. So it actually gives you more reaction conditions. So I give you some basic conditions here, but you do need to know that you have to have some acetone, and this is happening at a cold temperature. So be sure to add this part here to your reaction conditions. This is a general reaction. This is a more specific, so be sure to include that. And what's going to happen is I'm going to form a hexanoic acid. Again, you haven't learned how to name carboxylic acids, but I'm sure you can see what happened was the Al ending for aldehyde becomes an oic acid ending when you have a carboxylic acid. So one of the most common reactions you're going to do in an organic lab is a Tollens test. You're going to make a Tollens reagent, and this is a qualitative test for aldehydes. So when someone says something is a qualitative test, that's a visual. You're going to get a nice dramatic change that you can see during the reaction to see the changes of the before and after. So if they say it's a qualitative test for aldehydes, then that means a reaction change means that is an aldehyde. So a qualitative test for aldehydes means yes, you have an aldehyde if you see a reaction. So they wouldn't, for example, call this a qualitative test for ketones because ketones do not react. That's why it's a qualitative test specifically for aldehydes. So one of the simplest methods for oxidizing an aldehyde is to use silver ion in dilute ammonia. This oxidation produces a shiny silver metal mirror deposited on the walls of the reaction flask. So I have a picture of that over here. So you're going to be doing this in class. You're going to actually take Tollens reagent and you're going to see a silver mirror formed in your test tube. And this is how they used to make mirrors. So let's take a look at the reaction. You have an aldehyde. We have silver with our oxygen. And we also have in here dilute ammonia, water, and ethanol. So there's a lot of reagents that go, or a lot of pieces that go into making a Tollens reagent. In fact, in lab, you're going to be making the Tollens reagent fresh and then using it. So it's this hydrogen right here, the acyl hydrogen, that is going to be replaced with an OH group. It's going to make a carboxylic acid, but the other product is the solid silver, and that's what's deposited on the wall. So that is a qualitative test or positive test for aldehyde. Now, because this is an awful lot of stuff to write and Tollens test is so commonly used, a lot of times instead of writing all this information, they will just put silver plus because it is an ion and Tollens solution instead of writing all of this stuff. So if you want to write the abbreviated version, make sure you have silver plus on the left-hand side, but silver solid on the right-hand side. That still needs to be included in your reaction if you want to write it that way. So this is an oxidation reaction, because notice this starting carbon here in my aldehyde has 2 bonds to oxygen, and over here as a product it now has 3. So this would be an oxidation reaction. Remember, aldehydes undergo oxidation because of this hydrogen right here that can leave. Ketones don't have that. There's a carbon there. So aldehydes undergo oxidation and ketones do not. Another oxidation reaction of aldehydes is to use what's called Jones reagent. So Jones reagent has the CrO3, sulfuric, and acetone. So again, instead of writing all this stuff with the arrow, which they can do, sometimes they'll just write Jones reagent. And again, it's an oxidation reaction where this hydrogen becomes an OH group. Now the Jones reagent, I want to mention this. Jones reagent doesn't give us anything, any kind of change. So it's not a qualitative test. The Jones reaction is simply just taking our aldehyde to carboxylic acid because maybe we want the carboxylic acid instead. So keep in mind, Jones oxidation, Jones reagent is not a qualitative test. Again, I now have a second qualitative test, and this is Benedict's reagent. So we have Tollens, that's a qualitative test for aldehydes. We also have Benedict's reagent that is a qualitative test for aldehydes. So what happens is you get a red precipitate of copper oxide, and this tells us whether we have an aldehyde or not. So the reaction here, we start off with a copper 2 plus solution, we get a copper 1 solution. The beginning copper 2 plus is actually a blue solution, and when it undergoes its reaction to become a copper 1, it becomes a red precipitate. So this is a nice qualitative test to tell us whether or not we have an aldehyde. So again, qualitative tests tell us yes or no if it's present, versus Jones, this is also an oxidation, the other two are oxidation, but all we're doing is converting it from one to the other because we want to use it for something else. We're not actually using a qualitative test. All right, time to put what you learned into practice. Predict the following product or products for the following. Go ahead and pause the video, come on back, and check your work. Okay, to start this off, one of the things I like to do is see what compound I'm working with. This first one here is an aldehyde. This is an oxidation reaction, and I know aldehydes undergo oxidation, so yes, this will form a product. And the product's going to be, this H here is going to become an OH, and I'll have a silver mirror, so solid silver. All right, this is Jones reagent. Jones reagent is an oxidizing agent. This is an aldehyde. An aldehyde will undergo an oxidation reaction. And what's going to happen is, and this is a line structure, I wanted you to practice that. What happens is you end up getting an OH here. Notice you have to draw that line there because it's an understood H here. That becomes an OH. So I wanted to also present a line structure to you so you can practice those. And then in letter C, this is a ketone, and this is Benedict's solution, which is an oxidizing agent. This is a ketone. Ketones do not undergo oxidation, so you should not have written a product. It should be no reaction.